Okay. This week we're going to cover all of the material in chapter. Well, not all of the material, but the material in chapter 6. I think it's called PVT Experiments. There's 3 fundamental kind of things that are done in the laboratory. The first is to do a quality control or a check on the samples that were collected. We talked about that last week. And those samples during transportation could lead to, there could be leakage, basically is the main concern. If there's leakage from the samples that have been sent from the field into the laboratory. So we're basically checking if some kind of leakage occurred during the transport. To the lab. So the second thing, once they have a sample or container or samples that they feel are non-leak samples that represent what were actually collected in the field, then they'll start by doing some kind of a compositional analysis to get an idea of what was in the samples. In particular, they will look for the amounts of methane, ethane, non-hydrocarbons, nitrogen, CO2, and if you're not lucky, H2S, and all the various compounds and the amounts of those compounds. We've already talked about compositions. We've got basically masses and weight fractions, mole fractions, if it's a gas phase or if it's an oil phase, and so forth. These different analyses. So which compounds and how much of each. By the way, I think I probably made the comment when I talked about components that are in reservoir fluids that in the North Sea we're lucky not to have much H2S in the reservoir fluids. I think if I didn't make the comment, I should have probably. But just recently I've become aware that H2S, albeit in very small quantities, is found in production wells in the North Sea. But apparently that's related to the injection of water and the kind of creation of H2S in connection with injecting water and chemistry that kind of goes on between the water and the injection and the water in the reservoir, and then all of a sudden this H2S shows up. So there are smaller quantities of H2S, and apparently it's a problem, an issue that has to be dealt with. It's something I wasn't really aware of. But the in situ H2S content in the North Sea is basically nil. So we're lucky. And then once we have the compositional analysis on these samples, we kind of know what's there. The company who sent the samples to the lab will make a decision about which experiments will be conducted, pressure, volume, temperature experiments will be conducted on those samples. So we have duplicate samples, so we won't obviously measure the same PVT experiments on both duplicates of the samples, and we have a selection of basically four different types of standard experiments that can be conducted. I'll just, won't get back to this until maybe on Thursday, but basically you'll have what's called a constant composition expansion type test. I'll just get kind of the names out here. Constant composition. I don't know, experiment or expansion. I'm not sure what the E stands for. Experiment. That's where they put the sample inside a high-pressure PVT cell. PVT cell is just a high-pressure container. It may or may not have a visual access, meaning that you can see what's in the container. Most PVT cells today do have windows of some sort, so that you can actually measure the amount of gas and oil in the cell at a given pressure and temperature. But this CCE is the first type of test, and it'll pretty much, if you're going to do any experiment on a sample, it'll probably include this CCE. And then we'll have the next one that I think I'm going to talk about will be what I'll refer to as the SEP. This is probably a multi-stage. It could be a single stage, but I'm not going to. That's actually, I'm not going to talk about that type. The multi-stage surface separation. You guys already have done calculations on separation at the surface, and some of you actually went and did a two-stage separator calculation because I told you it would get you a job. I think I suggested that might get you a job. But anyway, these multi-stage surface separation tests, and then the third type will be a test that's conducted only on oils, called a differential liberation. Sounds like Bernie Sanders, liberation, revolution, you know, a new America. That would be probably a good thing. Experiment. This is again conducted only on oils. It's conducted in a blind PVT cell. You don't need to see what's inside it. And then the final PVT experiment is called a constant volume depletion test. So at least you kind of know if you're given this job, you're as a young engineer to do sampling and do the recommend PVT tests. You kind of know what you're going to be dealing with. So when the samples get to the laboratory, you're going to start this line of communication with the laboratory. They're going to do these QCs of the samples. And they'll be reporting back to you, oh, this sample looks good or doesn't look good for this and that reason. We're going to talk about what the QC tests are. That'll be kind of the first line of communication with the laboratory. The oil company who's operating and who's sending these samples to the laboratory will need to be in kind of a verbal communication with the lab technician. Okay? So that's kind of what we're going to cover this week. Any questions? All right. So the sample QC, if you have there are different types. If you have separator samples, that was one of the sample types that we talked about. It was, I think, the second one. Separator samples, 20-liter gas container and a short of 1 liter oil separator oil container, and we'll probably have a duplicate of each, 2 of each. And we might take separator samples, if it's a 3-day production test, you might take 2 sets after 24 hours, another set after 36 hours, and then a final set at the end. You might actually have like 4 or 6 of these bottles times 2. Well, let's see, that would be maybe 3 sets of the bottles times 2. So you might have a suite of these separator samples. So the QC for the separator gas, okay, basically we had, the flow line of the gas is flowing through the pipe, out of the separators back here. Separators back here, and we've got this gas flow line here, and then they insert a needle, some kind of a needle into the, I think that needle is pointed downstream. So the gas is flowing along here, and then they have this 20-liter container. And the pressure at this condition of sampling is very close to the separator pressure. Okay, there's not really any, shouldn't be any pressure losses between the separator and the point of sampling. So this container, this evacuated on vacuum container is filled, and it's filled with gas. And then there's a valve here that will be closed when they finish filling the container. And they fill this container up to the pressure in the line. So basically the pressure and probably the temperature, pretty close, are going to be the same as the separator conditions in the container when they close the valve and disconnect it. Okay? That's what it should be. So we've got this vessel, this separator, and then we got this. Separators don't look like this, but I'm not a good drawer, so it's just the way it is. Okay? And we've got some oil down here, which is, of course, being taken out down at the bottom. And again, I'll make some kind of ridiculous drawing. So we're taking these samples here. So what they're going to do when they get this sample to the lab, the sample container, the lab should bring the container to separator temperature. They probably won't, but they should. And then they'll simply I'm going to draw this. You've got this. This is the top of the bottle. They'll connect some kind of a pressure gauge onto this. Okay. And then they'll open the valve and measure the pressure inside the container. Okay? So basically, and they call this the opening pressure. The opening pressure. So they just put a valve in, open the valve, and then measure the pressure. What pressure should that be approximately equal to? Approximately equal to separator pressure. And how close it should be, well, it depends whether or not the lab actually brings it to the separator temperature or not. Maybe if they don't, then they'll do some kind of ideal gas correction. Okay? Let's say that the temperature in the lab was not equal to separator temperature. Okay? Then we could probably say from the ideal gas law, I mean, as an approximation, that PV equals nRT. So P over T should be a constant, right? nRT, no, Z. So PV nRT Z. So we're going to kind of assume that, that remains constant out there, that remains constant, and that's not too dependent on the temperature difference between the lab and the separator. It could be. So what we're going to kind of say is that, and the volume is constant of the container. So I think that if the pressure over the temperature in the separator is approximately equal to the pressure over the temperature in the lab, then you can assume that the volume number, that the number of moles is the same. Okay? So if that's approximately equal, then things are okay. Now, if the temperature was cold enough, you might be condensing some liquids out. So some of the moles are actually as a liquid, and it won't have the same pressure because you'll lose some pressure as those compounds become liquid, right? So you have fewer moles as a gas phase. So the pressure could be a little bit low if the temperature is low for that reason. That's really why you should try to have them bring the temperature to the separator temperature. Okay, so that's the first QC. Any questions about that? Okay, now I can't tell you that if the pressure they measure is like 1 bar less than the separator pressure, it's okay. If it's 5 bars, or if it's kind of like I'm not sure when you would say that there's been leakage. But let's say within, I'll just give you a number because you want a number, and I don't know, there's not a number out there, but I'll say if it's within 5%, it's probably okay. 5% is a good engineering number. If I say 10%, you know, but you've got two samples, so take the one that's closer to the separator pressure, right? It's probably the better sample. So let's say within about 5%. Okay, now the oil comes out here. I guess it goes through some kind of a meter, and then I think we collect the sample downstream to the meter. Maybe it's upstream, I'm not real sure. So this is our separator oil sample.
But if it's downstream, it won't be the pressure of the separator, it will be the pressure of the line.
Yeah, that's probably true. If there's some pressure difference between these, so maybe, yeah, you're probably right. Okay, I'm not going to bet any money on this one, but I'll go with you. Let's just say that it's taken. Say we take upstream to the meter. Okay, all right, it's probably right. So we've got this thing again. We've got a valve on here that will close, and we've got this thing full of oil. And again, it's probably at separator pressure and separator temperature. So when the lab gets this container, the QC on the separator oil, so what do we know about this oil here? Well, we know that this oil should be in equilibrium with the gas, right? So there should be kind of equilibrium between the gas and the oil, right? This is something that's real fundamental. We should have already got it when we talked about pressure temperature diagrams and inside the two-phase envelope, but maybe we didn't emphasize it. If a gas and an oil are together and in equilibrium, if I take your bottle of water, I don't see, he's got his bottle of water, it doesn't have much water left. If I take his bottle of water, if you just shake it enough, then the air in that bottle and the water in the bottle are saturated, they're both, it's in equilibrium, right? But you have to maybe shake it, okay? When that's the case, that water is at its bubble point, okay? That water is saturated. So if you have a saturated oil, the oil, by definition, is at its bubble point. It's anywhere in the system. It's down the reservoir, it's in the separator, it's in the production pipe. If you've got gas and oil flowing around, mixing around together, they're in equilibrium. The oil, by itself, is at its bubble point. Okay, it's fully saturated with gas. The gas is fully saturated with the oil. So the gas is at its dew point, okay? So anytime you've got two phases together in a system and they're in equilibrium, the gas is at its dew point and the oil is at its bubble point. Fundamental, okay? That's just going to be that way. So we know that the bubble point of that oil at the separator temperature should be equal to what? Should be equal to that separator pressure. So what the lab does in a very simple test is they'll take a little bit of this oil and they'll actually measure pressure versus volume for that separator oil. This will be the separator oil at the separator temperature, okay? And they'll take it to real high pressures, this may be separator pressure, okay? They'll take it way out here and they'll measure the oil volume, and as they lower the pressure, it just barely increases here, but then they expect to see that jumping up like that. And why is the volume getting so big here? It's because gas is coming out of solution and it's much more compressible. Okay? So what they're going to be looking for is this discontinuity here, and that should be right around the separator pressure. Okay? Yeah.
But isn't it the idea of the separator is to have a single phase?
It is a single phase oil. We're only measuring the oil itself. If you collected gas together with the oil, then you're not going to have that bubble point. Okay, we've collected just the oil. That oil is directly in equilibrium with the gas, so that if we bring that oil to the separator conditions, it should be at its bubble point.
That oil sample it's a single phase, right? But it's
Well, the bubble point is single phase. It's infinitesimal amount of gas. You know, so it's, yeah. It's 1 minus epsilon single phase. It's two phase. Depends how you see it. You can't see epsilon, so it's single phase. Okay. So this is the QC for the lab on the separator oil sample. Okay, and again within 5%. Okay, plus minus 5%. If there's leakage, it's probably going to be low. Okay, I mean it could be a slow leak, but you've got two of these samples. So the fact that both sample containers would leak, it's probably unlikely. Okay.
Why does the volume increase again? Because of the gases coming out of solution?
Yeah, that's right. Because when you go below the bubble point, you get some of the molecules becoming gas, right? And that gas is much more compressible than the oil. So that those molecules that become gas, they start, they get big elbows. So they use a lot more room than the liquid. So what's happening here to the oil volume, if you just plot in green oil volume, the oil volume starts shrinking here. And the difference between these two, that's gas. And gas, as a function of pressure, is it's increasing inversely proportional with pressure. So it's taken off. Oil's shrinking a little bit, but the gas is really taking off. So the total volume is going to be increasing. And you'll see a discontinuity in the pressure volume relationship. Okay. You won't see it in his water. So that's those are really the only two QCs that are done. Okay. Now, for bottom hole samples, conventional, what else basically is you have oil. In the old days, and it could be an MDT. I don't think they do this out in the field. I don't really know too much about out in the field. I went to one I grew up. My dad was drilling oil wells and stuff, and I didn't have to. It was fun going out on the weekends. These little fields in Oklahoma, and I got to play around as a kid. I wasn't learning engineering, so I was just playing around. But I saw a lot of oil-filled equipment when I was a kid. But I realized early on that I didn't know how to fix the machine. I didn't, I was clumsy. I wasn't going to be doing manual stuff. I had to be at a computer, okay? So thank God we got calculators when I was in high school. So that's kind of what I ended up doing. So I don't really know what they're doing out in the field. I went one time to an offshore platform in Norway, the Statfjord platform. Now, why did I do that? I didn't want to go to the platform. My wife didn't want me to go to the platform. And certainly the people on the platform didn't want to see me. So why I was out there is only one reason. It's because my dad was still alive, and he came to Norway, and he says, you know, if you're ever going to do anything for me, you know, before I die, is get me on a platform. I mean, he wanted to see a big platform. So, of course, it's illegal. So I had to find the guy in Statoil who, you know, bends the rules, you know, like that. And he took us out on the platform. I was scared to death. My dad was just like, died and gone to heaven. I mean, it's like the scale of North Sea oil and gas field versus Oklahoma is like, it's big difference. And it was just monstrous. And, you know, he had the time of his life, and I was just scared. The helicopter was going to flip. And so anyway, we got back on. So I don't really know what they're doing out in the field. But what they used to do with these traditional bottom hole samples of oils is that in the field they would actually make a similar test to this pressure volume test and look for a discontinuity. They would actually try to measure in the field a bubble point pressure. Not at reservoir temperature, because you know, you're at the top, you're at the surface. You know, in Saudi Arabia it's 140 degrees Fahrenheit, and you know, and in the North Sea it's, you know, 40 degrees minus C. So what they would do is they'd go in and they'd measure same kind of test very crudely. They'd measure volume versus pressure at some ambient temperature, and again it would look something like that, and then it would start jumping up like that, and you'd get this point of discontinuity. And you'd call that the field bubble point. Okay, the field bubble point at ambient temperature. And then they would write that number down and send it with the sample to the laboratory. And then the lab would do the same test. Okay, and it would be at the ambient temperature of the field. And they, you know, within 5%, or let's say, and make sure that the bubble point in the lab was approximately equal to the bubble point in the field. Again, we're going to say plus or minus 5%. Okay? And that was the QC. So if the bubble point in the lab was much lower or enough lower, that would say there was leakage in the transportation. And again, probably you have multiple bottom hole samples so that maybe one of them didn't leak. And you'll end up with at least one valid bottom hole sample. So that's the QC for oils. This does not work if you have an oil with a high gas oil ratio. Okay? It doesn't work for an oil with a high gas oil ratio. And I'll draw what it would look like this here in the field if we had, I'm going to make it orange. If we had a higher GOR oil, and probably we're talking greater than about 1,500 standard cubic feet per stock tank barrel, which would be about 300 standard cubic meters per standard cubic meter, if you're into SI units. Okay, so what you would see is that this line would look to go something like this. Okay, so maybe the bubble point, I don't know, could be in here somewhere. I don't know, could be there. You know, we don't know what it is. Let's say the bubble point was there, but what you would see is that it's kind of curving above the bubble point and below the bubble point, and that's because even as a single phase liquid above the bubble point, it's quite compressible. Okay, it's still quite compressible. So the volume is expanding, not linearly like this, but you're kind of giving you know, it's kind of curved the whole way. So you can't see any break point, any discontinuity. Okay, so that's the deal. And it's also usually at a higher pressure, so you can't really visualize this break. So it doesn't help. Okay, so that's those are the lab QCs. Any questions? Okay. So if I chose to ask you a question on sample QC in the laboratory, the only question I could ask you is, why do you do it, right? And what would you say?
Ensure there is no leakage.
To make sure there wasn't any leakage. That's it. Okay, I might ask you, how do they do it, but that's the bottom line. You need to remember that. Nothing else, remember that. If you were lucky, I would remember to ask you that question on the exam, because that would be kind of an okay, fair question, but I will forget to ask you that question, I'm sure. It's just like, I think everybody should probably just remember it, but it's actually a good question on the exam. So. Okay. So now we're done with that. So now we're going to talk about the next step in the laboratory procedures. Okay, step 2 in the lab procedures is to measure compositions. So what that means is the amounts, usually in mass, and they'll probably convert them also to moles for you, of each component. And of course you'll have the standard set of, the non-hydrocarbons, nitrogen, CO2, H2S if you have any. These are the non-hydrocarbons, and of course methane, ethane, propane, iso and normal butane, iso and normal pentane, and then these are kind of the pure compounds. Okay? These are the pure compounds. And then you get a bunch of isomers, a bunch of hydrocarbon isomers, until we get out to about C11, and then they quit trying to identify which isomers are in C11. They get tired, or there's too many of them, or it's not enough of them. So they give up. So these isomers are between C6 and C10 typically, maybe C9. And then you'll get C11, C12, C13. But don't think that C12 is just like pure normal dodecane. It's not. It's got normal dodecane in there, but it's got other stuff, okay, as well. And that'll probably go out all the way to C, I'm just going to call it N plus, to some heavy amount, okay? And what they're generally speaking measuring in the laboratory, in this equipment we're going to talk about after the break, is mass amounts. And then they convert them to moles by knowing the molecular weight. Okay? But, so, there's kind of a historical, you may be working on a field, because, Norway, they don't find enough oil fields anymore, so even you Norwegians, they're going to ship you off to some, who knows where, around the world, in your job, and you may be looking at PVT reports all the way back from 1960, 70, 80, 90, it's like good wine. The best stuff is, back there, the old days. Old is good, right? No, I'm not. And so the compositional analysis changed from the 60s and 70s until today. Okay, so I'm going to give you a picture of that. So if we look at what was the CN plus pre-1980, it was C7 plus. That's it. They didn't even give you how much benzene or toluene or anything was. It just gave you total C7 plus. And then in the So probably in the 80s, we got up to about C10 plus, maybe C12 plus. In the 90s, probably we're in the C15 plus, what you would find. You maybe even see in the late 90s C21 plus. Now, in the 1980s, they could actually do analysis out to C20 plus if they wanted to. I mean, they could do it. It's just it was expensive. You needed more sophisticated equipment, and the laboratories wanted to make more money, so they didn't do it. This is also the period where we're looking at more and more into more complex fluids. So we're looking at gas injection methods. You also have complex reservoirs like Stuttfjord, Ekofisk. You had Smerbuk were being discovered, and they had these compositional variations with depth, and they were very complicated and stuff. So you had a lot of, let's say, more complex fluid phase behavior, where if you didn't know the amounts of these heavy components, then you couldn't really predict it. You couldn't model it. Okay? So you had this stuff going on. And then after 2000, probably we started getting C30 plus, and then into C36 plus. That's kind of where we're at today. Probably it'll stop there, I'm guessing. Most lab reports today will give you the amount out to C36 plus. So just so you're aware. And this bunch of isomers, this thing here, that started in the 80s and 90s, where they started splitting out the benzene and the toluene and the xylene and these other isomers. So in addition to the amounts that they would give you, they would also give you a molecular weight estimate, or measured, but probably estimate, and a molecular weight of the heaviest material, and maybe even a specific gravity of that. Okay? So they could be measured or calculated or back calculated from measurement. So these are definitely got some uncertainty to them, for sure. Guaranteed probably with no better than 10%, 10, maybe 15% for different reasons. This one is probably better than 1%, probably. Unless you have a very, very strange oil, a very, very aromatic oil, or very, very paraffinic oil. When I was in India, I found out that oils there were incredibly paraffinic. It was kind of interesting. I know some, like, Asian countries have paraffinic oil, but they had, like, really paraffinic oil, and they had a lot of wax precipitation problems. So
The 1% you're talking about the
accuracy.
specific, for the gravity. The
Yeah,
accuracy.
yeah, because they don't measure it. It's back calculated. Okay, I'm going to get to that, but they back calculate it. But so it could even be more than 1% in accuracy. But and sometimes they don't even report this. They should, but they. Okay. If it was C7 plus, we're basically measuring these values. These values are measured. Okay? If it's C10 plus and greater than C10 plus, then these numbers, these two numbers here, are back calculated. And the accuracy gets worse and worse the heavier you go. Okay?
Which type of value add is it to get this C10 plus?
How do you do it?
Or what is it, what kind of balance?
The magnitude?
Yeah.
Okay. So, these values here, for a given CN plus, 10 plus, or 30 plus, okay, they can vary. I'm saying for a given, whatever you want to call it, okay, can vary considerably from your reservoir to your reservoir to your reservoir to my reservoir, okay? So actually it can be quite different from reservoir to reservoir. So I can't really give you a common C12 plus molecular weight. It could be anywhere. It's going to be more than C12 molecular weight, but it could be as low as that. C12 molecular weight would be what, 150 or something? 12 times 12 is what, 144, and then add on a little bit. So around 150. It's going to be more than 150 for C12 plus, but it could be 180, could be 230, could be 300. Depends how heavy the oil is. It's a good question, but it just has a wide range of answers. So what you could say is that the molecular weight of N plus, the only thing that's for sure is that it's greater than the molecular weight of CN. Okay? And if it was a light gas, that might be what it is. Basically, C12, that's all. Doesn't have much anything heavier. But it could be much higher. And then if you happen to have some reservoir Curtis, just call it my name, which happen to have 195 C, I don't know, C10 plus molecular weight, okay? And reservoir Singh, since I've been in India, pick a common Indian name. This might be 195 too. But the specific gravity here could be 0.846, and the specific gravity here, being an Indian field, could be 0.792. Much lighter, more paraffinic. Okay? Yeah.
This is because of the isomers, right?
It's because of the isomers, yeah. If it's a waxy, then most of the hydrocarbons are alkanes, and if it's aromatic, then they've got a lot of cyclics. So this would be more paraffinic. Maybe this is kind of normal, which has got a little of each, And then some other reservoir might have reservoir. Let's see, aromatic oil. I'm not sure where. Where do you want to go? I'm not sure where to go. Aromatic oil. Where would like to go? Some nice island with oil, a lot of oil, right? Job security and good weather and Southern California. Let's say there's LA. Okay, so it's got 195 too. Don't start thinking that all C10 plus is 195, but it's okay. And this guy could have, 0.892. Okay, aromatic. Okay. So, all right, so that, I think, burns up our first hour. The point is that we're going to measure compositions, but in addition to these amounts, they're also going to give you some information about the molecular weight and density of this heaviest stuff. Okay? All right, take a break.